In this module, we will introduce the concept of quasi-likelihood estimation. Quasi-likelihood estimation will arise in several contexts for your syllabus. You shall also see it in the paper on longitudinal data analysis. For this paper, the context is overdispersion. We have seen that it is possible to conceive counts where the empirical mean and the empirical variance do not appear to be similar. If the variance exceeds the mean, then we have a situation of overdispersion. If it is less than the mean, we have a situation of underdispersion. This is not restricted to counts only, but it can happen for any member of the generalized linear model family where the nominal variance is different from the model specified variance, which is specified by the variance function. Several remedies are possible in this case, such as using alternative parametric families if these are readily available, or using something called a sandwich estimator of the variance, which is robust to the parametric specification. And finally, the concept of quasi-likelihood estimation. We shall explore this concept in more detail in this module, introduce the quasi-likelihood function, and see that it shares some properties with the maximum likelihood estimators. Learning objectives for this module. We shall first redefine the concept of overdispersion. Next, we shall see an application of techniques for overdispersion in the context of the physician visit data. We shall go more deeply into the technique of quasi-likelihood estimation, which we know is one means of modeling overdispersion. Quasi-likelihood estimation leads to estimators of the regression coefficients and not of the scale parameter. So finally, we shall look at a method of moments-based estimator for the scale parameter. Overdispersion occurs broadly when the nominal variance exceeds the model-based variance. This means, say for example, we have a generalized linear model and hence automatically a variance function. The variance function gives me an estimate of the model-based variance. However, suppose, say we have a categorical predictor. In that case, it is possible to group the outcome by the levels of the categorical predictor and to find the sample variance as well as the sample mean within each of the categories. This is termed the observed or the nominal variance. In the situation where the nominal variance is seen to exceed the model-based variance, we have a case of overdispersion. If our outcome is a count, this means that the nominal variance exceeds the nominal mean. In case of proportions, this would mean that the observed variance is greater than that specified by the model-based variance, which we know to be n pi into 1 minus pi. Just as we can define overdispersion, we can also define the concept of underdispersion. So, in this module, we shall be concerned with both situations, that of overdispersion as well as underdispersion. Broadly, our situation is that the nominal variance does not match the model-based variance. We have seen in a previous module some examples of situations where overdispersion can arise. The first example is when we have clustering in the population. So say we are looking at the prevalence of some genetic trait, and instead of looking at a random sample of individuals, we observe a population where the individuals are clustered into families and then look at the proportion within families. We can average these proportions to get an overall estimator of the prevalence within the population. However, such data will be prone to clustering, as we would expect the prevalence of the genetic factor to be similar within members of the same family and to be different across families. We have seen that clustered counts or clustered proportions can lead to a situation where the variance is not the same, but rather exceeds that specified by the normal, binomial, or Poisson variance. Overdispersion can also arise when we have subject-specific effects. This means, say for example, we are observing a count, and instead of having a situation where the rate parameter for the count is similar for all individuals, we have a situation where each individual can be assumed to have his own rate, which is not fully explained by the measured covariates, and that these rates also have another distribution across the population. So these can lead to distributions such as the beta binomial or the Poisson gamma, and we have seen that these again lead to overdispersion. Finally, overdispersion can also occur when the number of observations which we observe is not fixed by design but is random and has a probability distribution. Now, these three cases of overdispersion are rather unique in the sense that we know why the overdispersion occurs and hence can arrive at a parametric model for the overdispersion. So, for example, in the case of subject-specific effects, we could choose to use the beta binomial distribution for inference rather than the binomial distribution. There is also a fourth case where overdispersion can arise, and in fact, underdispersion too can arise in this situation, and this is when we have observational data. Now note that for observational data, we do not really know the true mean, but rather only the fitted mean. So for example, if we have model misspecification, say due to the fact that we have omitted a rather important covariate, we would not expect the observed variance and the model-based variance to be the same, and thus would have a situation of overdispersion. Let us first consider a recap of overdispersion using the physician visit data. Deb and Trivedi have analyzed data on 4,000 odd individuals covered by Medicare. The data is available from the data archive of the Journal of Applied Econometrics and also as an R dataset, debtrivedi.rda, in the Journal of Statistical Software. So the objective for this dataset was to model the demand for medical care in terms of the number of physician visits, in terms of covariates such as the health status variable hospital or the number of hospital stays, health, which is self-perceived health status, the number of chronic conditions, as well as socioeconomic variables like gender, school, and private insurance indicator. So here we see a histogram of the physician visits, and we can see that there is a lot of variation in the data in the sense that the number of physician visits has a very long tail. We can also perform more exploratory analysis of the data. So here we can look at the outcome by covariates. In this case, by the covariate OFP, the plot to the left is simply a scatter plot of the data, while to the right, the number of chronic conditions given by OFP has been categorized, and we can see from the box plots that there is a lot of variation in the data, and that it does not appear that the mean and the variance for this data set would be identical. So we would expect a situation of over-dispersion. The first technique which we apply to this data set is the standard technique of Poisson regression. So here we have used the GLM function to fit a Poisson regression to the data using family equal to Poisson. So note that this means that we have used the canonical link, which in this case is the log link. So here is the outcome from the Poisson regression, and you can see that there is a line below the set of coefficients which says that the dispersion parameter for the Poisson family was taken to be 1. A second alternative is to continue to fit the Poisson model, but to use robust estimators of the variance. This can be used by using a set of estimators called sandwich variance estimators. The idea between sandwich variance estimators is that they are robust to the model specification. So we can get these estimators by using the command coeftest fmpois, which is the GLM object, and with the option vcov equal to sandwich. This returns a z-test of the coefficients. If you compare the outcome from here to the previous outcome, you will see that the estimates are similar, but that the standard errors and consequently the z values and the p values have all changed. A better alternative is to fit a model called Quasi-Poisson regression. So this has been done on this slide. So here we are using, as before, the GLM command, but instead of saying family equal to Quasi-Poisson, instead of saying family equal to Poisson, we have said that family is equal to Quasi-Poisson. We have not specified the link, so note that the default link for the Quasi-Poisson family is also the log link, and by running the summary command on our object, we get, as before, the set of coefficient estimates, standard errors, t values, and p values. Note that there is a line below the set of estimators which says that the dispersion parameter for Quasi-Poisson family was taken to be 6.706. So contrast this to the outcome from the Poisson family, which said that the dispersion parameter was taken to be 1. This means that Quasi-Poisson regression assumes that the variance function is not necessarily equal to the mean, but is equal to some scale parameter commonly denoted by phi times the mean, and from this data we estimate phi as 6.706. As this is clearly greater than 1, we have a situation of over dispersion. Before we go into quasi-likelihood estimation, which is the underlying technique for the quasi-Poisson option for the GLM family, let me, for the sake of completeness, mention an alternative parametric option, which is fitting negative binomial regression. So this can be accomplished within the GLM framework using glm.nb, and the syntax for this is given on this slide. As usual, it leads to a set of coefficient estimates, standard errors, z values and p-values. Note that the dispersion parameter for the negative binomial family is taken to be 1. We have here a comparison of the estimates from the 3 sets of procedures, that is, the maximum likelihood estimators of the regression coefficients from the Poisson regression, the quasi-Poisson regression, and the negative binomial regression. In general, they are quite similar. However, if you compare the corresponding standard errors, you will notice that there is a difference. We shall next go into the details of quasi-likelihood estimation. First, let us look at the motivation for this technique. Now, let us suppose that we have outcomes for whom the true distribution is given by some distribution function g. Let us also suppose that if instead of g, we were to apply some distribution capital F, then the score equations under capital F are given by summation I1 to m SIF theta m hat equal to 0. We are assuming here that we have m individuals, that the distribution F is indexed by some parameter theta, and that SIF is equal to del log F del theta is the score function corresponding not to the true distribution G, but to the distribution F. We have then a result that theta m hat tends to theta star, such that expectation under G, which is the true distribution, of summation I1 to m SIF theta star equal to 0. Thus, the estimator theta m hat is asymptotically normal, and it can be shown that root m theta m hat minus theta star tends to the normal distribution with mean 0 and a variance of the form A inverse B A. For the details of the matrices A and B, you are referred to the paper by Wedderburn. The quasi-likelihood technique was introduced by Wedderburn in 1974. He defines the quasi-score function given by S beta, assuming that the parameter is beta, equal to summation 1 to m SI beta, where SI is the contribution to the score function from the ith individual. Assuming a GLM, this is equal to summation I1 to m del mu I del beta prime variance inverse yi beta phi into yi minus mu I beta equal to 0. Now, in saying that we have assumed a GLM, I mean, however, that we have only assumed the form of the variance function and not that the GLM holds in the sense of the parametric distribution. So, in fact, the quasi-score function is derived from a function called the quasi-likelihood given by q of mu y equal to summation 1 to m integral yi to mu I y minus t by a phi vt dt. We shall use this quasi-likelihood and the score functions from the quasi-likelihood to derive our estimators of beta. Note that construction of the quasi-likelihood function Q only requires us to know V as a function of t and thus does not require any parametric distributions. So to repeat here, we are making no distributional assumptions. We are only assuming that expectation y is mu I of beta, some known function of beta, and that the variance function variance of yi is given by vi equal to a phi into v of mu. Key properties of the quasi-score function are expectation of Si equal to 0 and variance of Si equal to minus expectation del Si del mu I. These key properties ensure that the behavior of the maximum quasi-likelihood estimators is quite similar to that of the maximum likelihood estimators. We use quasi-likelihood estimation to get estimators of the regression coefficients. However, we are also interested in getting an estimate of the scale parameter, and this is traditionally derived using a method of moments estimator, which states that A of phi hat is equal to 1 over m minus p summation I1 to m yi minus mu I hat square by v of mu I hat. You will recognize the term in the numerator to be the corresponding Pearsonian sum of squared residuals. In this module, we have introduced the concept of quasi-likelihood based estimation. For this paper, quasi-likelihood based estimation arises in the context where we have over-dispersed or under-dispersed data. The concept of quasi-likelihood is due to Wedderburn, introduced in a 1974 paper, and it is a more general concept. The idea is to define a function called the quasi-likelihood function, which closely mimics the properties of the likelihood function and hence leads to estimators with some attractive properties. The quasi-likelihood function can be defined in terms of the mean and the variance, and thus construction of the quasi-likelihood function does not require us to specify anything more than the variance function, which specifies how the variance is related to the mean. This means that we do not make any parametric assumptions. However, say for example we define something like v mu equal to mu, which we know holds for the Poisson family of distributions, and it turns out that the distribution of y is indeed Poisson. In that case, the quasi-likelihood estimators will reduce to the usual maximum likelihood estimators.